Welcome to the next lecture on the finite element method, and this is going to be the direct extension of the last one in the sense that we are starting to handle the problems that occurred in the end of last lecture when we've seen that for certain problems our standard FEM doesn't really work. So this is also the kickoff for some additional advanced FEM lectures. So after concluding the most simple FEM scheme that you can think of, we're now talking about additional things that you can do to improve and make your software more powerful. The topic of today is called Divide and Conquer. So we're talking about divisions and subdivisions and refinements of grids. So we're trying to optimize our grid structure suited for the problem. For example, for those singularly perturbed problems that we've seen in the last lecture already, but also in general, we're talking about local refinements and suitable data structures for adaptive grids. The agenda for this is, firstly, we take on where we left off last week with the singular perturbations. We're trying to describe the problem more in detail, and then I'm going to show you the so-called Shishkin-Type grids. These are, well, probably the most simple idea when you talk about local refinement. So they sound very troubled and cryptic. Well, actually, it's a very, very simple and intuitive concept. And it's one of the ways to resolve those singularly perturbed problems. And it's also the initial idea that gives you a hint on why and how this whole local refinement thing makes sense. And then we're talking about adaptive grid refinements, firstly in general, and a bit more in detailed motivation. So not just about the singular perturbations, but also about general problems that need adaptive grid refinements. And then we're talking about bisection. This is going to be the algorithm of choice when we locally refine grids. And we're talking about recursive adaption. So what to do with the grid in practical if you actually want to do some refinements. And then the next big step here on the agenda for today are data structures. The reason for this is that, if you talk about adaptively refinable grids, it's not always the best way to go for the trivial type of storing your grids. We're going to discuss two different approaches there and see advantages and disadvantages and give you a short guideline on how which one you should choose when you actually have a practical problem. And then in the end, some short conclusions and outlook. Okay, let's pick up where we left off. So we start by talking about the singular perturbations, and as a beginning short problem description, we're not going to do the full mathematically detailed description, but only in a qualitative way, because this is only a side note here and not the core contents of this lecture. So you can essentially do a whole lecture series for one semester just about those singularly perturbed problems and what to do with them. But we're just going to touch them because they're like an illustrative example of the problems here. So you see, if you have a standard Poisson equation as your problem with a small factor there in front of your Laplacian, but in the sense still a standard Poisson equation, you could also multiply this factor on the other side, and then you would have minus Laplacian of u equals 100. Nothing problematic here. And then if you solve this on a rather coarse uniform grid, everything works out perfectly. You get a smooth solution, you get your typical bulb-shaped solution for the membrane bending problem. Everything looks perfectly. But then if you add a convective term, so a first order term transporting the quantity in a certain direction, and you still use that same grid, suddenly everything looks terrible. So not only does it not capture the solution behavior properly, which should be similar to this one, but only shifted into this direction of the vector. this makes the shift. But what you get here is more or less a discontinuous solution, so it's a spiky behavior. It just doesn't represent any, it has nothing to do with the actual solution of the problem. Yeah, and what's the reason for this? Well, if we have a convection term, we can run into situations where it not only quantitatively changes the solution in terms of a slight shift, but it gives you a whole different behavior and sometimes even ruins the whole solution behavior. And to understand this, we have to look at those terms more in detail. So you have your second order term with the Laplacian here that has a rather small factor. And on the other hand, you have your first order term here. And the factor in front of this is 10, so in the terms of a magnitude, it's rather big. At least it's not big in absolute terms, of course, but it's a factor round about a factor 1000 bigger than the second order term. And that gives you exactly the reason why we're running into this problem. As this first order term is dominating so strongly, we are approximately in a case where we only have a first order problem. So because of this strong dominance, in comparison to this first order term here, this is roughly 0. And as you probably all know, a first order problem cannot fulfill boundary conditions on all sides. We have talked about this in a rough way last week already. If you think about those simple one-dimensional examples, for example, like u prime of x is equal to some, let's say, constant right-hand side, u prime of x equals 1, then, well, you cannot couple this like on some interval a, b, and you cannot couple this with two boundary conditions. So you can't just require u of a equals u of b equals 0. And the reason for this is simple. If you try to solve the equation, then you would say, okay, u has to be something like the integral of my right-hand side, so the integral over 1. And the primitive of the constant 1 function is the function x plus some constant alpha. And here's the important part. It's just one constant. So if I want to fulfill a boundary condition on one of those two sides, I can definitely do that. So if I want to fulfill the boundary condition, let's say I'm case A, I only want the boundary condition on my left side, so u of a equals 0, then I can simply choose alpha equals 0, and I get u of x is just x. Well, that is in derivative, it's 1, and the boundary condition on the left side is also fulfilled because u of, obviously that was not exactly correct, so let's say I'm in a more simple case, but the rest works similarly, so I'm just on the interval 0, 1. And then I can choose alpha equals 0, and yeah, I have this as my solution. And if I'm in the other case that I want to require my right-hand side boundary condition, I can also do that, and that gives me the fact that alpha has to be chosen -1, so the solution is x minus 1, and then if I insert my right-hand side, I'm still good here. But I cannot require both of them, right? So you cannot have a function that has derivative 1, so a constant slope of 1. It cannot be a boundary condition on both sides. And that's exactly the same thing that's also happening in 2D. So if you have this almost first order problem here, then you cannot require boundary conditions on the whole boundary. You can only require boundary conditions on part of it. And that leads you to the concept of the reduced problem. So now, after saying, well, this is my almost first order problem here. And if that's the case, well, then I'm concentrating on the actual first order part of it. So I'm removing, to get my reduced problem, I'm removing my second order term. I'm only considering this first derivative here. But I also have to restrict my considerations to the boundary. And we call this part of the boundary gamma r, named after gamma regular. So that's the part where everything behaves in a good way. And we're choosing this half here. So in a sense, half of the boundary, so the bottom left half, you could say. And then you can solve this. You can solve this problem here, so your first order problem, with half a boundary condition, and this gives you this solution. So I've used this same grid that gave me total crap before, and I'm getting a perfectly fine, smooth solution. And why is that? Well, because now I have actually only required half a boundary condition, and that's perfectly fine for my problem. So it has no problems fulfilling this half boundary condition. And you see here what the natural thing for the solution is. It's going up here, so it's not going down to 0 on this right side. So if I add my full boundary conditions here, then I have the problem that my solution wants to go up here, and I'm forcing it down to 0, and that creates this numerical instability because the solution just can't do this. So why is this reduced problem interesting? The reason is that we need to identify the boundary that causes problems in comparison to the boundary that doesn't cause us problems. And for that, the reduced problem is helpful because we can take it and use it to look at the solution and find out where do we have problems on the boundary, which is obviously the case here, and where is everything smoothly. So this gamma r is this side here, where everything goes perfectly. So yeah, in the end, we want to get back to our original problem because we don't just want to solve a different thing, but we need to do something near the boundary. And the boundary where we need to do something is this part up here. So there is one half of the boundary, the gamma r, where everything works perfectly smooth. But here we are having problems, so we need to do something. And yeah, of course, the rough idea would be to say, all right, well, if my grid is too coerced to capture the whole solution behavior, I could simply globally refine my grid. And that's what I've done here. So from there to there, I've drastically increased the grid spacing. So from, I think, 10 subdivisions here to 30. That, taking a factor 3 in your number of subdivisions in each direction gives you a factor of 9 in terms of total points, and that also makes the system a bit more problematic. So in total, we had 20 times longer computation time. I've tried to measure it, and well, it looks a bit more like a shifted solution, but it's still so spiky, it's still not working. So I had a 20 times longer computation time, and the solution is still terrible. So it still does not look good. So this rough approach of the globally refined grid cannot be the answer for those problems. The idea when we talk about this is, and I've already hinted this, we're doing a local refinement near the problematic boundary. So we leave the grid as coerced as it is, close to the original regular boundary, and we do a local refinement near the problematic one. And that idea is called Shishkin-Type. So it was named after a mathematician who originally created a bit more specific type of local refinement for singularly perturbed grids, but capturing the general idea of doing a fine grid near the singular boundary and the coerced grid and the rest of the domain, that's always called something like Shishkin-Type. So first, in order to do this, you consider the reduced problem just like we did before. So you leave out the second order term and just keep your first order one. And yeah, you also remove half of the boundary conditions. Of course, you might wonder, what is a good way to choose this gamma r? Well, it's in a strict mathematical way, it's not very simple to say this, but in a rough rule of thumb type of way, it's not very difficult. If you have a domain and you have your convection field B, and then this B is a vector field, it looks always something like this. And a good way to choose your regular boundary gamma r here is to take the side of the domain where the vector field is coming from. So you would always take the back end of those arrows as your gamma r. The reason is that if you look at the solution behavior, when you have a convection, it always pushes the quantity in a certain direction, so in this corner up here, and that causes the stiff the stiff behavior and the strong descent of the solution close to this boundary. That's why, rule of thumb, choose the side of the domain where the wind is coming from, so to say. Then you can also always try it out. So you just fix this gamma r and then you try out if everything works, and if the solution looks perfectly smooth, then you probably have made a good choice. And then you divide your boundary into the regular part, gamma r, and the singular part. So that's the part of the boundary where the singularity occurs. And then you're almost done, because you simply say, okay, well, I make my grid coerce in most of the domain, but I'm making it very fine close to the singular boundary. So you simply you take your whole domain and you fix a boundary layer. So you simply say, in this case, I took 0.75 here as the border, and I said, okay, well, in terms of all my x values, the last quarter of them is considered to be the boundary layer. Of course, you can also adapt this, and the same is done here also. And then I've simply created a piecewise uniform grid. So I've simply changed the way that I'm computing those points that form my grid. So instead of just taking a linspace from here to here with, let's say, 10 divisions, I'm doing a linspace from here to here with 5 divisions over a long distance, and then I'm doing the other 5 in this short area. So it's simply not globally equidistant, but only in a piecewise way. And of course, there is different ways how you can achieve this locally refined thing. In the original Shishkin grids that the mathematician invented, the grid was getting finer and finer the closer you approach this boundary layer. So you had very coerced cells, and with each step they were getting smaller, so that you have a super high resolution here and a very low one in the rest of the domain. But yeah, in the simplest case, if you want to create a Shishkin-type grid, you can simply say, I take a piecewise uniform thing, take a coerced grid away from my problematic boundary, and a fine grid close to my problematic boundary. And that is it. So that is already the first concept of local adaptivity, because we have adapted our grid to the needs that our problem has. So our problem has a singularity occurring at this problematic boundary here. And so we said, okay, well, we know that there is a problem at this boundary, so let's do something about it. Let's make the grid finer so that the solution is able to adapt to the boundary conditions much better. And that is that. So yeah, you still keep an optimized number of degrees of freedom. So compared to using a global spacing this fine, you're saving probably I don't know, a factor of 5 to 10 of degrees of freedom here. So that's huge increase of performance. But still you keep the high resolution at that part of the domain where you actually need it. So that is kind of this balancing between performance and accuracy. Now we want to transfer these concepts that we have just introduced, finding out that there are certain problems that need a locally refined grid, and transfer them into a more general concept towards adaptive grid refinements. And firstly, some observations to capture this in a more mathematical way. What follows now is concerning Poisson's equation, so simply minus Laplacian of u equals some right-hand side. We're using a uniform grid, so what comes now is for a uniform grid with a step size h here, and we're talking about linear discretization. So basically the type of finite element method that we have implemented so far. So on the one hand side, there is quality. If you increase the mesh resolution, then you get a better approximation. Not only is this intuitively clear, but it can also be proven in a mathematical way. So we will be talking about this in a few lectures. It's called the convergence concept. So if you look at the solution of the exact problem and your numerical solution, UH, for a certain step size, then the error is decaying in a certain way if you reduce the step size. So if you, for example here, reduce h to 1/2 h, so take twice as many divisions in each direction, then your error will be multiplied by a factor 1/4, right? So it's h squared here and some constant. So it has to be seen in a qualitative way. If you reduce your number of steps, then your error is also cut by a certain factor, and usually that factor should be bigger. So if I take 1/2 as my step size, then it should be 1/4 or even more than that. So that's the good part. Taking more grid points gives you better approximation. But there is also complexity. Higher mesh resolution requires additional effort because the step size is dimension-wise. So if I have my original, let's say very coarse grid here, just one cell, and I take half the step size in both directions, then I replace my original 4 points by, well, 1, 2, 3, 4, 5, 6, 7, 8, 9 points. So roughly a factor of h squared, or 1/h squared. So if I'm taking half the step size, I get 4 times as many points roundabout. And that's a huge problem because I have a linear system that is 4 times bigger. And that's why you always have to balance between how much quality do you need and how much complexity can you handle. Because it's not trivial to go from a linear system with 100 equations to a linear system with 400 equations, or maybe 1,500. So yeah, reducing your step size has drastic impact on the computational costs here. So you cannot take the best out of both worlds. You cannot have quality without also taking your complexity. But we still want to try and get at least in the direction of it. So we want to preserve as much quality as we can while still keeping the complexity down. And the way we do this is just like in the singularly perturbed problem cases. We're adding information about the problem and use this to create locally refined grids that give us the quality of approximation because it's fine grid where you need it without taking a huge complexity because we're not using uniform grids that give you a factor 4 if you have a smaller step size. So yeah, to capture this concept of before again, what you see here is not exactly the behavior of a singularly perturbed problem, but it's still the diffusion convection type deal. And if you look at the solution here, it's shifted in this direction, but the grid doesn't really match this thing. So the uniform grid never takes into account how your solution looks. For example, the fact that up here there is almost nothing happening in your solution, but still the grid has a fine, the same resolution up here compared to down here, where you have a strong descent in your in your solution. So even if you don't stumble across an actual behavior of singular perturbations and this numerical instabilities with those spiky solution behavior, it still always makes sense to consider locally refined grids because they just capture your solution behavior better. And yeah, to make this whole thing a bit more drastical, I have another example for you. What you see here is one time step of the Allen-Kahn equation. It's a time-dependent problem, so you have a time derivative involved here. And then essentially this is a reaction diffusion problem. So you have your diffusive term here, and you have a nonlinear reaction. So this doesn't involve any derivatives here, but it's a power 3, so it's a cubic polynomial. But still, it's a reaction diffusion problem. And in particular, this factor epsilon here in front of the Laplacian is a small factor. So this problem is used for phase separation processes. So for example, you can imagine putting some oil into water, then this will always demix. So the oil and the water will split into two phases, and you would in the end have a lot of oil in combined at the top of the water, and then the rest will be just pure water, but the drops will always vanish and combine to a huge combined phase. And that's what Allen-Kahn is doing, but that's not so important here. What you see here is after a certain number of time steps, Allen-Kahn is combining all the mass of those two phases. So you can imagine this blue color here, solution value -1 to be the water. And then you have some, I don't know, some chemical, maybe oil or something else. That is value 1 here. So you have a lot of water, a drop of oil that has formed after some time, after the demixing has happened. And this solution behavior is in that sense special, that there is a huge part of the domain where there is simply nothing happening. So you have this huge part here after the demixing has happened where there is pure water. So nothing is going on there, nothing is diffusing, nothing is creating. There is just a constant phase of water with nothing to be done. So you probably don't want a fine grid resolution in this part. But then if you look at this, at a zoomed picture here, then there is a very steep gradient, and in particular the gradient of u scales as this small factor epsilon here. So the gradient of u is round about as steep as your epsilon, which is usually in the range of something like, I don't know, 10 to the power of -4 or 10 to the power of -2, something like this. So it's a very, very steep gradient. So you probably need a lot of grid refinement to actually capture this behavior. So if you roughly speak about this, you would want to have like super big grid cells here, up here, because there's nothing happening. But then you want very small triangles, and even smaller than this, to capture this behavior in the middle here. And well, to get this picture with a uniform grid, so if I don't have any adaptivity and want to capture the whole behavior, I would require around 1,000,000 degrees of freedom. So I would have to take 1,000 times 1,000 points in each direction to just here be able to actually capture those gradients and get this type of picture. But that's kind of pointless because it just takes so much time to solve a system of this size, 1,000 times 1,000. And also it's complete nonsense because in most of the domain we're not doing anything. So we can get to points where for certain problems, uniform grids are not only a bad choice, but they are like a really bad choice because it's just not doable to solve the problem with it. Imagine solving a time-dependent problem like this with a system of this size in each time step. That's just not happening. So yeah, there is problems that are even more complex than those we have seen before because you just cannot do it on a uniform grid. What you want to do instead is you want to consider local grid adaptation. So you see here a zoomed in picture at this part of the domain. You see here that the grid is very fine, close to this interface where the actual gradients are happening, but it's getting coerced down here because there is just constant 1 as the solution. You don't need anything here. And you're also getting more coerced up here because there we are going towards the constant -1 phase. And to look at the big picture, you're seeing very large grid cells up here, so this big, right? And you have this circle here in the middle where the grid cells are that small that you can't even see them individually in this unzoomed picture. And that grid here was the one that was actually used to produce this picture. And that has around 8,000 degrees of freedom. That's still a huge number, but if you compare 8,000 to 1,000,000, that's more than a factor of 100, and it's still giving you those results. So sometimes you need those highly local grid refinements, especially, or for example, for those phase separation problems. You need a very fine grid where the solution gradients are large and a coerced grid where nothing is happening. And then you can get this accuracy without needing to increase your complexity that much. And that's exactly what you want. So some open questions here. The first question is where to refine. So we have seen examples, for one, the boundary of singularly perturbed problems where we had steep descents. Also regions of large solution gradients in general, like those phase field. So this Allen-Kahn method that you've just seen. But it's also possible to create adaptive schemes. And we're not talking about this here. So these schemes are based on error estimation. So essentially during runtime, you try to estimate the error on individual parts of the domain and try to find those areas where the error is large and refine your grid there. That's called adaptive error estimation. That's done in the PDE numerics lecture. So they are discussing how this can be constructed. And of course, the other question, and that's the one that's interesting here, is the question how. So how can you actually get this locally refined grid? One example have we seen already, this Shishkin-Type grid that was just doing a piecewise equidistant division of your domain. So very fine, close to the boundary and coerce and the rest. That is very simple. But of course there is others. So one famous type of refinement is the so-called red-green refinement. I will give you a short idea of what this means later on. But what's important here in our lecture is the bisection method. And that's what we're going to do today. So we talk about how does bisection work when you want to refine grids. So you see of those many questions, we're only answering essentially one. And the reason for this is that you could do a whole lecture just about adaptivity for FEM, and you would maybe not even be done within one semester. So there is just so much to talk about. We're focusing on the one detail, and that's the bisection. What does that mean? Well, the idea is very simple. You take a triangular cell, you cut it in half. So that's bisecting your triangle. What does it practically mean? It means that you define a refinement edge. In this case, it's this one down here. And that should be defined as a particular one. So we'll talk about this in a minute. So you define a refinement edge, then you add a new node in the middle of this edge, and then you remove the old cell and replace it by two new ones. So that's as simple as it gets. So there is no way of doing a refinement that is simpler than bisection, because you cannot do less than cutting into two. Just a quick reminder about this. We talked about that part of shape regularity already when we constructed the grids, but I want to mention this here again because it's very important. Shape regularity says that for all of the cells in your grid, you have a single one constant C, such that you can bound the longest edge from above by the constant times the in-circle diameter. What that means is that a triangle like this, where you have, I don't know, this distance as your in-circle diameter and the longest edge just, I don't know, 4 times longer, that's perfectly fine. Then you would have C equal 4. Or in the way I've written this here now, it would be 1/4. But then you don't have this triangle and also a very long stretched one, because those long stretched ones have a very longest edge, and the in-circle diameter is very small. So then you probably cannot bound this number from above by this rho t. Okay, why is that important? Well, you choose the longest edge for refinement. That's the thing I just mentioned. So it's always important to choose the longest one for refinement. And that's now finally the explanation why we, in the beginning of the grid creation, said that we need to introduce a particular numbering scheme such that we always know what the longest edge is. Here comes the reason, because we want to use this edge for refinement. And then if we do this, the shape regularity of the mesh either remains as it is, so your constant C just keeps the same, or it gets better. Look at this very long stretched triangle here that has a very long edge and a very small in-circle. And then if you choose this side down here as the refinement edge, put your new point here in the middle and cut this in half, then you see that those newly created triangles, they are better. So the shape regularity of them is better, because if you put the in-circle here, okay, that's not a circle, it's an ellipse, but then the longest edge of this is only half of what the original longest edge was, and the in-circle diameter has remained more or less the same. So your constant is getting much better, and if you do this adaptively again, then you would, after one step, arrive at almost perfectly shaped triangles, and that's very good. If you don't do this, and if you would, for example, take this triangle and now use this shorter edge for refinement, then your triangle would get even more longly stretched, right? You would have this longest edge still down here, but your in-circle would even shrink. So it's very important to fix the refinement edge to be the longest one if you do bisection. But here comes another problem. So let's say we have a very, very simple grid that consists of only those two cells. And we want to refine this one. So we just want to refine this one because our error estimation has said, well, there is something to be done down there. And we only want to refine this one because we want to have optimality in the number of degrees of freedom, right? We always want to keep it as low as possible. Now let's do bisection. And we have a problem here. Because after bisecting this triangle, we have two new ones and we have a so-called hanging node. It's called hanging because it's in the middle of the edge of this triangle here. So there is an edge here, and this triangle does not have a vertex where this point is. And that simply cannot happen. That is not allowed in our discretizations because we need to always be able to identify global and local indices. So remember when we talked about this DOF mapped, we always said that, well, for every global degree of freedom, we need to be able on every cell of the grid to identify the vertex that it corresponds with. So if you have this red point here now and go into this triangle here, say T0, then this is a vertex. If you go into this other triangle, this is also a vertex. You can always identify it. But if you go here, then you simply cannot do that. So you cannot identify the global with a local index, and that's just not working. So this cannot happen. What's necessary is we need to refine the surrounding triangles after having refined something locally until there are no more hanging nodes. And the case that we have just seen is the simplest case, because here, if you look at this upper triangle that we now need to recursively refine, then this edge where the hanging node is the longest edge. So that is the refinement edge. And then it's simple, because then you can simply say, okay, I have my triangle with the refinement edge, the hanging node is on this refinement edge, then I can simply say, okay, then also cut it. Right? You need one recursive refinement because you simply also divide that other triangle. And then you're golden, because now those two newly created, let's say, faces of your triangle are always ending in vertices or in points of the grid here. So that's not problematic. But you can also have another case, and this is the more problematic one, if the hanging node is not on the refinement edge of the adjacent triangle. And that's the case here. Let's say we have this situation of a grid and we want to refine the green grid cell for whatever reason. Well, you can already see if I'm doing this refinement, then I have a hanging node here, this one. But this is clearly not the refinement edge, because the longest edge of this triangle is here. Never get to the idea of refining this as is. So you cannot just cut this triangle in half like this, because then you are not preserving your shape regularity. Your triangles are getting terrible, and that's just not allowed. Okay? So never do this. What you instead need to do is you need to recursively refine them until your hanging node is on the refinement edge. So if I now mark this green triangle to also be refined, because we have a hanging node there, we need to do something, then the next step is to use its own refinement edge and simply cut it in half. Okay? Now this bottom triangle here is perfectly fine because it doesn't have any hanging nodes, but it still has the hanging node in the smaller one up here. But now we're in a good situation, because now we see that this hanging node is on this smaller triangle on the refinement edge, because now this edge is the longest one. So now we can do what we wanted to do before and do the cutting here. But we have an additional problem, because we have now refined this way, we have created another hanging node down here. So our next triangle is also marked green, in a sense that it needs to be refined because we have a hanging node. So we can go one step further. Okay, up here we simply have connected those two. Now this is turned brown because it's perfectly fine. And well, we also have refined this big one down here. The left side of this is perfectly fine because it doesn't have any hanging nodes. But here in the middle, you still have one. But now that's the same situation as before. It's on the refinement edge, and you can do the cutting that you wanted to do. So I'm now cutting this way. And then we are completely golden, because now we don't have no hanging nodes anymore. And what's also very important, we have not ruined the shape regularity of those triangles, because they are all still in the same shape as they were before, just smaller. So there are situations when you need more than one refinement to get from one side to another. You should never forget about the shape regularity, especially in those cases, because it would have been just tempting to do a cutting like this. It's not allowed, because it completely ruins your grid, and in the end you're making more damage than you have made good. And what I've made here in green color is very important concept, because it's called the marking. So if you do local refinements of grids, you always need some sort of marking strategy in the sense that you need to say which adjacent cells have to be refined and which don't have to be refined. So yeah, sometimes multiple refinements are necessary to regularize your grid again. But compared to choosing just a global discretization reduction, because, well, if you want this as a step size, then you would have to do this everywhere, right? You would have to divide all your cells here into this fine of a grid. So compared to that, it's still a huge improvement in terms of efficiency, what we have done here. But sometimes still you need to refine, sometimes not only where you want to, but also where you need to. And that's something you have seen in this phase field example in the beginning. So the mesh was getting coarser as the further you got from the interface. So that's has something to do with the recursivity. Now you know everything there is to know about how to refine a grid on a piece of paper by drawing new lines. That is nice, but we also want to do this in your computer. So you need to know something about data structures and how to practically do this. And for that, there is one way to go, and that's the direct storage. That's essentially an extension of what we have been using the whole semester. So you need an array for points and an array for cells, and you introduce an order such that the refinement edge is directly clear, in the sense that it's, for example, between the second and the third point. So that's the way we created it. We always said that the point opposing the longest edge is the first point. And then, well, if you take your order like this, 0, 1, 2, then the refinement edge is always between index 1 and 2. And that's kind of cool, because if you have this cells array here with those 3 columns, right, then you always know that, well, between this and that we have the refinement edge. So if you have something like this here with some weirdly given coordinates, that's also something you have to get used to. Then your points array is simply 4 times 2, because we have 4 points and dimension 2. And cells is a 2 by 3 matrix, because we have 2 cells and every cell is a triangle. And then the refinement edges on cell T0, T1, so here's T0, that the refinement edge is between point 1 and 2. And for T1, it's between point 2 and 1. Nothing happening here. Now, if you actually want to do the refinement, then what do you need to do? You need to add a new point, and you have to replace one cell by 2 new cells. So in terms of the points array, it's just an appending, right? You put something here, and for the cells, you need to also, cut something out and introduce something new. And that looks exactly like this. So you do a cutting of the bottom left triangle, you add a new point here, so the middle point of the refinement edge, and you replace this original line 0, 1, 2 by 4, 1, 0 and 4, 2, 0. Of course, this hasn't spoken about recursive adaption. So after this step, you would of course have a hanging note here. So you would then have to recursively refine this one too. That means that you would also replace this line by 2 new lines, but we're not talking about this here. But if you talk about direct storage for bisection, it always means you add points and replace lines in your cells array. Okay, that's a very simple approach because it directly takes what we have used for creation of those grids and works with those data structures. The advantages are pretty simple. You have, in a sense, a minimal memory consumption because you just exactly store what you need, just as before. You store all the points and cells, and that's still given. The implementation is rather simple because you only have to add something to an array or replace something, and all information is directly available just as before. So you can handle this grid just like a uniform one, even though it's not anymore. Okay, but it also has disadvantages, and that's interesting here. Changing array sizes is actually a very costly operation. So for usual programming languages for arrays, for example, also in MATLAB, in Python here, or in C, if you change the size of an array, that's not very good. So arrays, in comparison to lists, are static data structures. They have a fixed size, and usually when you want to change their size by, for example, adding a point, that means that the computer has to create a whole new array and copy everything that was there before. So that's a huge copy operation. And if you think about grids with, let's say, 10,000 points, that's a whole lot to do. Neighboring relations, which can be important for some other types of finite element methods. So there is finite element discretizations with more advanced approaches compared to our piecewise linear one, where you explicitly need to know which cell is a neighbor to which. So you would explicitly need to know that 0 and 1 are adjacent over this edge. And yeah, well, if you do a refinement, then you would have to explicitly, freshly compute those neighboring relations again, because if you do this division, then you don't really know, well, after this step of dividing, you have, I don't know, maybe T0 here, and T1 was this, and T2 is this. How would you know that T0 is now a neighbor of T1, and T2 is now a neighbor of T1, and so on? So you explicitly have to compute them after refinement. And what's interesting here too, in some processes, you need to also coercion your mesh again. Think about this phase separation thing where we ended up having one droplet in the middle. These things usually start with so many individual small drops everywhere in the domain, and then in the end have focused phase here in the middle. So in the beginning, you would need to use fine grids around all of those drops. But of course, over time, you want to coercion them because you don't want to have residuals of this fine grids here after a long time, when then here you only have constant -1. So coercioning is an important task. But if you have a direct storage and you have simply deleted your old cells and added new points, well, then coercioning is just either very complicated or not doable, because you would have to know which points you can remove, and so that it still makes sense as a grid. So that's a very complicated task. And there is another idea how we can store this data, and that's called the hierarchical storage. And that's it sounds a bit more complex in the beginning, but actually it's a super smart approach. And the concept is we start from one very coarse macro grid. You can always think about, in the simplest case, just having 2 cells, or maybe, I don't know, 5 times 5 or something very simple. And then when refining, you not only store the current mesh, so you don't just delete the old cells, but you store all refinement steps. And to do this in a bisection type way, The perfect data structure for this is the binary tree. So what's a binary tree? Many of you probably have heard about this before, but I'm going to do this in a short interlude. Trees are always drawn like this. A tree node is something, so some abstract data object that has three things essentially. It has a pointer to 2 or less children. So if you look at one of those nodes here, they have pointers telling me that this is my child and this is also my child. A tree node also has a pointer to a parent. So it also knows that this is my parent. And of course, the tree node always stores data. For other applications, you might store letters, words, numbers, and we will see what we're storing here. So a tree node has pointers to children and parents and the data. And then you have special nodes. This one up here is the root because it does not have any parent. And you have leaves because they don't have any children. Okay, and then the applications are, for example, search trees. So binary trees can be implemented for very efficient search in structures. It can be used for building heaps. So a heap is part of a sorting algorithm. So you can build a very efficient sorting for numbers, for example, using binary trees. Or they can also be used for hierarchical grids. And of course, there's a ton of other applications. I'm just naming a few here, but we are, of course, concerned with the hierarchical grids. So what are our nodes? Well, just like in every binary tree, every node has a pointer to parent and children. And the data is the vertices of one represented cell. So in every node, I am storing the vertices of the cell that I'm representing. So if you imagine a zoomed in binary tree, then you would have here, for example, something like the vertices of my represented cell. So for example, like, I don't know, 0.1, 0.2, and so on. So here, the data that I'm storing is those vertices. And then I have my children, and they again store some matrix with point data and so on. Okay, so every node represents a single cell. And now this whole grid is represented by creating one so-called macro grid, because it's very coarse, that is explicitly defined, for example, as a uniform grid that can be stored in a direct way. So you can, when I'm talking about macro grids, you can always imagine this grid that simply contains those two cells, and those two cells are written explicitly in direct form by saying, okay, I have those points and I have those cells. And now every macro cell is the root of a new binary tree. So from every macro cell, I'm starting a binary tree when I'm doing a refinement. And the current grid that I have is given by all the leaves of my binary tree for all of those binary trees, of course. Okay, let's look at this. Say we have our standard macro grid, and I have two cells. One is cell 1 and cell 2. Both of them have to store. So essentially what you're storing here is not just a number, it would be the coordinates of the vertices, right? But for the sake of shortness, I'm dropping this. So you have a very coarse macro grid with two cells, and you're creating them as the root of a new binary tree for both of them. And now you want to refine your grid. And when you do bisection, you create new grids. The indices for those new grids are added because you still need those original ones. That is a typo here. That should have been number 2. And they are added just like the way that the bisection was happening. So from my initial grid cell number 1 that was divided in this way, I created cell 3 and cell 4. And the reason for the coloring scheme is that 1 and 2, the original macro cells, they are now not leaves anymore. So the leaves are 3, 4, 5, 6, and those are also the actual grid cells of the grid that we're representing. So we still keep the information that 3 and 4 were created by refinement of number 1, but we're not representing them currently. And now if you say you want to refine them even further, then you would, for example, refine cell 4, and that creates your cells 7 and 8. 4 now becomes an inactive parent because it's not a leaf anymore, so it's not in our actual current grid anymore. But the current grid is given by 3, 7, 8, 5, 6. But we still have the information available that we had before. And what you see here is in essence both the advantages and the disadvantages of this hierarchical storage. So firstly, in terms of advantages, for tree structures there are huge libraries available because it's a very common concept in computations. So you don't have to implement everything from scratch. Most of it is already available. And then if you look at this here, again, coercioning is absolutely trivial. Because if I want to go back from, let's say, my cell 7 and 8, because I say I don't need the fine grid here anymore, then I can simply delete those nodes here, and then I'm back, and then I have my number 4 here. My information is still all there. If I'm removing some leaves, I still have the grid information that was there before, so I didn't delete it from my direct storage. Okay, so coercioning is trivial, and the refinement edge and also the neighboring relations, all of this is inherited from the parents, so I don't explicitly have to compute it because it's directly given. So I'm taking everything from my parents. For example, if I know what the neighbors of my parents are, then I can directly deduct this and use efficient search algorithms for tree structures. But it of course also has disadvantages because it takes larger memory, because you're storing all those nodes that you used to have and not only those that you actually have. And the implementational effort is also bigger, of course, compared to the simple direct storage way. To compare this, I have listed the advantages and disadvantages here again. So while the direct storage is very simple, the hierarchical is not so trivial. While you have everything available directly in the direct storage, you need to gather the information by tree traversing, because you need to find out what is actually a leaf in my tree, and that is current cell. And while direct storage only takes that much memory that you actually need, it's much more in hierarchical systems. So if memory is an issue, then you shouldn't go for this one. But if you have a method that needs neighboring relations, you are in a problem with the direct storage because you explicitly have to compute them, while in the hierarchical way, they are inherited from the initial coerced macrogrid. And coercioning is almost impossible when you are in direct storage systems, while in hierarchical ones, it's a very trivial task. You can just delete leaves and then you are back to the grid that you had before. So you should go for the direct way if you want to simply try it out. So then it's a good choice to work with our data structures. If your FEM is simple and you have piecewise linear approaches, you don't need neighboring relations, then it's also good. And if you know where to refine, for example, at the boundary of the domain for some singularly perturbed problem, then it's also good. If you want the most powerful thing, then you should go for the hierarchical storage. If your FEM requires neighbor relations, or if your grid changes dynamically and you need coercioning, then it's also a good way to go for hierarchical storages. And just some results here. That's another illustration of this phase field stuff. So like the Alan-Kahn equation that we had before, only with a slightly bigger cell in the middle now. And you see that it's possible to have this very fine resolution in the middle of the domain and a very coarse one up here. And you also see that there is a degradation in grid size going out here that comes from the recursivity and in refinement. So if I'm refining some cell here, it always affects my neighbors, so I can't just do hard cutting of the step size, but that's usually completely fine because it's very rare that you need a super fine grid right here, and one step further you can live with cells of this size. That's usually not the case. So recursivity naturally causes this this slow decay of grid size, but that's completely fine in most cases. So here you see how powerful local refinements can actually be, because those problems you cannot solve with a uniform grid. So some conclusions in the end and also an outlook. Firstly, conclusions, what have we talked about? We have seen that local grid refinement can be a very powerful thing if you want to find the balance between performance and accuracy, because you can gain accuracy in those areas where there is a lot of stuff happening, but still keep the performance by not adding unnecessary refinements. For an efficient local refinement, it's crucial to know something about the problem. Either you need to know that there is a boundary layer occurring in a singularly perturbed problem, or you have areas of large gradients versus areas of almost constant solutions, like in the Alan-Kahn phase separation deal, or you do some error estimation. That's also something you need to create before. You need to prevent hanging nodes if you do a recursive or by doing a recursive refinement strategy. Otherwise, your method is not well defined after refinement. Of course, aside of just preventing hanging nodes, you also need to prevent irregular shapes of triangles. So you always have to keep your shape regularity. And there are two main approaches for storing the grid information, and they have both different advantages and disadvantages, and you need to choose a good one exactly for your needs. What's open? So I said that we are not answering all the questions here, just a few of them. Oh, you shouldn't see this already. So how can we prove that this actually works? So it's clear by intuition that it is good to have high resolutions in areas where there is something happening and lower resolution everywhere else. It is not very trivial to mathematically deal with those non-uniform grids and prove that they actually work almost as good as a very fine uniform one. What we also haven't answered is what is needed to construct an error adaptive scheme. So we have only looked at examples where we explicitly knew where to refine. So it's not trivial to construct those, and so constructing good error estimations is a whole topic of itself. What could have been done differently? We could have used red-green refinement. That's what it's called. So instead of bisecting and simply cutting triangles in half, there is a different approach. It uses a combination of so-called green refinements and red refinements, which are basically our bisections. The advantage of red-green, as you see here, it cuts one cell into 4 subcells and then does a bisection. The advantage of this is that it stays a little more local. So it's easier to do a recursive scheme because you only exactly need to refine the surrounding cells and not many others. An advantage is that here you cannot use binary trees because you have 4 children. So it's more difficult to find a good data structure that's suiting. And of course, instead of using adaptivity in the sense of the grid, it's also possible to consider the so-called p-adaptivity. that means that where I need higher accuracy, I can also use a higher polynomial degree. So I can say on some cells I'm using piecewise linear, and then I'm going for piecewise quadratic and so on. That's also doable, but that's a whole other deal. It's still also sometimes named it's also named adaptivity. And I'm hoping that with this, you have got an overview of the concepts when talking about locally refined grids, and have seen how it can be done, where it should be done, at least some examples of that, and also what we haven't discussed as of yet.